Okay, we start with our lecture number 3. Before we start, I just have to say here we have Mariana. She's sitting there in the back. She's the last one you didn't met before. She will be taking over from next week, and she will be making all of you experts in separation, oil and gas, and water and oil. So let's just make. I think it's will be. Just if we make a very just like a summary, what have we covered so far? We're starting to look at each block. More or less what oil and gas processing contains. Okay, it contains all of these different processes, and that the goal is basically to deliver not on this class but on this class that we have to deliver products with a certain spec, okay, for different parts of the process. And when we talk about water, there are some things we have to take care of when we look into oil and we look into gas, okay, and depending in which part of the process we are. And then later we came to see to the central part on that process. That's the one I'm going to teach you these 2 weeks, which is separation and stabilization. Okay, we were looking more in detail into that box. And the way that's done is basically with a series of separators. And this separator, what we call is a train, okay, is the set of, I have either a first stage or a high pressure separator, medium pressure, and low pressure. Okay, this can change from platform to platform. Actually, I think I uploaded the reference material. And where will that be? Here. Okay. And there is one article that is from the Oil and Gas Journal. And it's an engineer. He was working with John Campbell John Campbell is one of the biggest training companies for processing, okay, for oil and gas processing. So he did a summary, and very nice summary, of what can you find in the North Sea. Okay, what kind of specs, what kind of processes, what kind of things are used in the North Sea. Okay, so I think if you have time, you should go and read. There gives you an overview of what kind of processing it uses, how many separators it's using, etc. For our case, in the Norwegian continental shelf, it can go up to 4 stages, but typically there are 3 or 2. Okay, and yeah, so we do it by placing, a sequence of separators where we extract gradually the gas from the oil, and that gas we compress it all the way to the line that goes to dehydration and then goes to for power generation, gas injection, gas lift, for export, whatever. And then we looked at how the process looked like, much more complicated. But I told you, if you have to try to first find the inlet and then find the things that are familiar, and from that, then on you progress, okay, with the rest of the diagram. Don't feel intimidated by that. We took 2, and I also gave you some material that I upload was on engineering diagrams. It's a book by Stewart, Surface Production Operations, and there you see the type of diagrams that you can find: block diagram, process diagram. That's what kind of a variation of that is what we were using. Then you have PID indicating instrumentation, and then you have other type, plot plan, and then you have isometric. So just very short, 7 pages, but gives you an overview of what kind of diagrams we can find. Okay, and lastly, we were going to say what do you need, okay, to basically that process gives you, in a very rough way, gives you how much gas and how much oil you're going to have. Okay, and you need a few things, and that's what we are going to look more in detail today. Uh, to be able to characterize, to study that process. But I told you that basically the components that are on hydrocarbon, oil and gas, and then I told you that it's like the fingerprint, okay? The name or the fingerprint of a certain fluid, you can do it by mole fraction, okay? If you have certain distribution of methane, ethane, propane, then that's the fingerprint of that fluid. That's going to determine how that fluid is going to behave, okay? So that's why it's important to keep what is mole fraction and also mass fraction. Sometimes you see some documents from some plant of some field. They are based on mass fraction, and you have to be able to change, okay, to be able to convert between them, okay. And that's how far we reached during last class, okay. So the purpose here, keep it in mind, we have to, one of them is to mechanically separate the oil and gas and water, okay. That's the first goal. Then the second one is to stabilize this oil and gas, such that when I continue further transportation, processing, whatever it is, you won't have further or not significant vaporization of gas from the oil or condensation from oil from the gas. Okay, that's the main goal. And the third one, which is more on the economical part, we want to increase the amount of oil. Okay, depending what we put here in this box. Okay, can be 3 trains, can be 2 trains, can be different pressure and temperature. I'm going to get different amounts of oil and gas, and sometimes they can be significant. You will have to work on that on an exercise later. But if you use one stage, you're going to get some oil and some gas. But if you use 2 or 3 stages, you're going to get different ratios, okay? And sometimes they can define, let's say you have a gas field and your main goal is producing gas, okay? But the oil and the condensate, you can sell it at a very good price. And that can probably affect very much the economy of your field, okay? Can help you very much on the economy of the field. Okay, so I want to make first a short comment on phase diagram. Okay, what do you understand about phase diagram? Phase diagram is like, first is okay, what kind of things do we have in the x and the y axis? Temperature and pressure, right? And then if it's, let's say, for a pure component, I guess that's what you have seen before, right, in some of the previous courses. How does it look like? No, that's too advanced, okay? It looks first like just a simple line, okay? Just a simple line that looks something like this, okay? And it separates the area where I have, so what do I have where? I have liquid, yes, and vapor. That correct? Yeah. And it's true that we don't use this diagram for many engineering calculation, okay? For that, we need some other things I'm going to cover today. But this gives you just a very good quality check of your understanding of the process. So this tells you if I have a combination of pressure and temperature that is here, okay, I'm going to have a vapor, okay. But if I have a combination of pressure and temperature, which is up here, I'm going to have a liquid, okay. However, that line doesn't extend forever, but there is a point, I reach a point that is called the critical point, right, where I have a TC and a PC, where is not, I don't have a clear distinction between what is vapor and what is liquid, okay? Maybe the properties are very similar. Okay, I have a liquid which behaves like vapor-like, and I have a vapor that behaves liquid-like, and I don't have such a sharp distinction between these two phases. Okay, below that point, I have a very clear, a very sharp interface. If I just change from one point to another, then I will have okay. And it's not also another comment is that it's not. It doesn't mean that it's what would you say if I have two phase, right? Yeah, maybe we can keep that for later. Okay. Now how? So that would be for a pure component. Pure component, a single component. Okay, pure component, single component. Okay. Now, when we have more than two multi-component, okay, that's typically what we have, multi-component mixture. Okay, the diagram looks significantly different. Okay, and one of the things, if we have two components, okay, well, we could say in a way you can see that we have the curve for one component and we have the curve for another component, single component, okay, but it creates some sort of an area in between. Okay, so here I have will be vapor, here it will be liquid, but here I have a whole area in between that I have a mixture, okay, of vapor and liquid. And you can think about that, that's what happens. And that's actually what we have in a multi-component mixture. Okay, it's going to look exactly, if I have two pure components, that area will be very relatively small. Actually, not like I painted here. Maybe something if I have, for example, methane and is something else. Okay, maybe it's slightly smaller size. Okay. But we have any general multi-component mixture, we have the following, okay? Okay. We have first to say that's liquid, okay? Or if we call it in a better way, is undersaturated fluid. Okay? Okay. Where we have purely liquid. On the right side, we have again undersaturated fluid, undersaturated gas, okay, on the right side. Everything that I have inside is in the saturated region. That means I have inside here, I have a mixture. Okay, so it's very simple to read. I have a certain pressure, a certain temperature, and if I cross the intersection gives me here, or here, or here, I can know very clearly what do I have. Okay, if I have a liquid, if I have a gas, or if I have a mixture. If I'm talking about this separation process that we have been discussing, where should be at the inlet of the separator, okay? Where should I have my combination of pressure and temperature? Should it be here? Should it be here? Or should it be in here? Okay. If I have this process, okay, where should the inlet be? Okay, the combination of P and T. Well, I should have a mixture, right, to be able to separate. So it should be simply inside this area. Okay. The other thing is that this diagram is made for a given composition, okay? For a given composition, okay? if I have any other composition, any other percentage that I'm mixing all of these components, okay? The phase envelope, okay, that's what I call the phase diagram or the phase envelope. It's going to look completely different, okay, depending how much I have. So it means that when I have my multi-stage process, okay, here I have one composition, right? But then it's not going to be the same as the composition entering the second stage, and it's not going to be the same as the composition entering into the third stage, okay? So we cannot analyze everything with the same diagram, okay? The diagram is going to be changing. But if, for example, we are looking at fluid from the well, from the reservoir, all the way before the separator, then we have a unique composition, right? Unless we have merging of streams, unless we have separation of streams, if it's the same fluid that goes from the well all the way before the separator, then we can use the same envelope, okay? But after that, after I start removing components, changing components, that's not valid anymore. Okay, now I have a few things that this point here is what we call the critical point. Just like what you have in a single component, pure component diagram, you have a critical point. Here you have the same. And the critical point is basically splitting. You have one line that tells you it's the saturation line. Okay, this line tells you. Well, this line tells you, just in the case of that, okay, I have here pure liquid, but if I start reducing pressure, okay, or if I'm here and I start increasing the temperature, I will reach a point where I'm going to get the first bubble of gas. Okay, just like when you're cooking water, you are increasing the temperature until I get the first bubble of gas. Okay, in that case, I call this the bubble point line. Okay. Bubble point, just try to remember, is when I get the first bubble coming out of liquid. Okay, I have pure liquid and I get the first bubble out of solution. Okay, I'm actually cooking and boiling out the gas. Okay, then I have the same thing happens with gas, but here what do I have in the gas side? Okay, in the gas side, I have, let's say, I have a gas, okay, and then I reduce temperature, reduce temperature, reduce temperature until I start to get some condensation, some liquid dropping out of the gas, okay, and that we call the dew point line. Okay, dew like morning dew, like condensation, giving you some idea on condensation is the dew point line. Maybe we should take this down, I think. Not sure why I made it here. Okay. Um, then we have these two. I'm not sure if you remember, but the first class we were discussing on the second class, we were discussing about for the gas. Okay, you have there are some requirements, right? That you have to have the Crickondon bar and Crickondon term. Okay, if you remember these two, that I say they have to be below 105 and below 40 Celsius. Okay, so the Crickondon term is here. Okay, and is the point, the most extreme point to the right. Okay, this point here is a Crickondon term. Okay, and this point here, well, not not like that, but in this case, it will look very similar to the critical point. Okay, this point here is a pre-condem bar. And that's what I told you. Basically, that tells you if you're reducing those two numbers, okay, you are like controlling the size of the envelope, okay? If you make it very, very small, let's say these two numbers that are very small, they tend to go to the left and down, okay? So it tells to scale down your envelope. That means that you have a bigger area of combinations of pressure and temperature where you simply have a single phase, okay, either a gas or a liquid. So if you reduce those two, it means that it takes you go much, much lower in pressure, much, much lower in temperature to cross that line. Okay, so that's related to that requirement of the gas that you have. Shouldn't have any condensate, any water, or any liquids. Okay, you should have pure gas when sending it through the pipeline. Okay. Yeah, I'm a bit afraid of putting more things on this plot, so let me just make a new one. Okay, and I have one more thing. Okay, so it's very simple. If it falls inside, I'm in two phase, but also I have some lines which are constant quality. And that's not so important. Okay, but quality means, so sometimes people use the letter X for quality. Okay, and that means number of moles of vapor divided by the total number of moles. Okay, if I'm exactly in this line, remember I have pure gas. Okay, I use starting a slight amount of liquid, but minimum. Okay, almost negligible is starting to come out. So here it will be 100%. Okay, 100% this quality. Here you will have 99%. Here you'll have 98%, and so forth. Okay, and that you are going to be able to draw with this program we are going to use in class. But keep in mind that this diagram, if you want to use it for something quantitative, then you have to get a diagram that has that has these quality lines. Okay. Still, we don't know how to. Okay, so far the way you would use the diagram simply to put P and T, and then to see where am I, and then just verifying. But that's the most it can help you. Okay. Um, yeah. Before we go into, let's talk a bit about. So if I'm talking about an oil reservoir, okay, the phase envelope looks the same if it's a gas or an oil. Okay, it looks similar. The thing is that is the starting point, where I am. Where do I start? Okay, if I'm talking about an oil reservoir, okay, then the pressure and temperature of the reservoir should probably be when I have just pure liquid. Okay, so it will be something like that. Okay, maybe let's put it a bit higher. Okay, so I have PR, reservoir pressure, TR, reservoir temperature. Okay, and when I flow towards the well, I reduce pressure, not temperature. Okay, so it will be the same. I go at the bottom of the well, and then I flow all the way up to the wellhead. Okay, then I lose some temperature. Maybe I go into the two-phase region. Okay, and then finally I go in the flow line, the transportation flow line, all the way to the separator, and I reach separator pressure here. Okay, P separator and T separator. Okay, So that's how, if we say, let's make a simple diagram of the well. Okay, we have a well that goes PR, TR, okay, then goes here, and then I have a pipeline, and then I have my separator, okay, all along this process. That's how it roughly looks like, okay. And where I intersect depends, what conditions, how high this is away from this line, okay. Sometimes it might be very, very close, okay. Sometimes it might be far, far away, so then I reduce pressure and temperature and I go inside the envelope. Now, if I have a gas, how does it look like? If a gas reservoir, okay. In that case, it's very similar, okay, but the initial PR and TR, they have to be in the gas part. Okay, so here I have PR and TR. They are in the gas section, okay, or in the gas area of the chart. And then the same thing, I go reduce down, bottom of the well, and then I go inside until I reach P separator and T separator. Okay, so in terms of how the envelope looks like, they don't look an oil and a gas. They don't look very different. Okay, they have all the points, critical point. They have the bubble point and the dew point. The thing is that the size of the gas part, okay, we are working, is much bigger in the gas reservoir, and is much bigger in the oil. The part on the oil side, on the liquid side, is much bigger. Okay, but it has more or less the same shape. Okay, so now let's see how. Let's go. Just keep that in mind, okay, and just keep that in mind. But let's see how do we make calculations, okay, of separation process. So we have one method that we're going to cover here, that is called equilibrium ratios. Okay, so let's call it here methods. Well, I have bad handwriting, but not so bad. So I think the oh let's use the name that it used. Okay, for performing. What we are going to do actually is performing flash calculations. Okay. Okay, basically flash calculation, or also we call it equilibrium calculations. Okay, basically we have a mixture, okay, we have a composition, and then we are somehow inside the envelope, and we want to calculate how much do we have of each, okay, how much vapor and how much liquid do we have, okay, at that, and that's essentially that's what I need for a multi-stage separation process. Okay, flash calculation or equilibrium calculation. Okay, so that's one empirical observation. Okay, so how people try to solve this problem, a long time ago. Okay, that was in the 40s, in the 30s. Okay, they tried to come up with a solution. Okay, so they made a plot. Just make sure that I get the scale correct. Okay, they define something, okay, that is called the equilibrium ratio. Equilibrium ratio. Okay, and the equilibrium ratio is defined by K. Okay, And that I define for every component, okay, for each component individually. If I have methane, ethane, propane, I have to make for each one of them, I have to define this equilibrium ratio, okay? So that's why I put Ki, okay? That means for component I. Okay, if I talk methane, it will be methane, propane will be propane, etc. Okay? And that is defined as the mole fraction of that component in the vapor, okay, that will be Yi, okay, divided by the mole fraction of that component in the liquid, that will be Xi. Okay. Where if I have, let's say I have a mixture, let's have a container where I have some liquid, and some vapor, okay, I have a mixture somehow, okay. I know this container has a composition called, we usually use the letter Zi, okay, is the overall mole fraction, okay. This one, that means, let's say, of methane, okay, Z of methane, C1, will be the number of moles of C1 divided by the total number of moles that I have in the whole container. You're looking at the whole container as a container as a whole. Okay. Now, Yi is if I take only the gas part, and then I say the number of moles that I have of methane only in that container divided by the total number of moles that I have on the vapor. Okay. So the total number of moles of methane that are on the vapor divided by the total number of moles in the vapor, and then I do the same for the liquid. Okay, so that will be N liquid C1 by N liquid. And this is the guy that I call YC1, and this will be XC1. It's very strange, okay? So you will see now why, but that's the way people develop it, and that was the most efficient way, okay? But they found this ratio between the two fractions for one component, and they did a plot of that. Let's see, maybe make it below, okay? We have space, so okay. So they made a plot which was very, very interesting. In that plot, they plotted this equilibrium ratio. First, they made it in log scale, and here they plotted pressure, also in log scale. Okay, that means that these units will be 1, for example. This will be 10. This will be 100. Okay, this will be 1,000. Okay, this will be 0.1, 0.01. Okay, and the same thing with pressure. Okay, we'll have 1, 10,000, etc. So they saw for each component, okay, that it has, first it has a linear behavior. Okay, it has like a linear part. Okay, that will be, I don't know, C1. Let's put here C1. Then you have C3. Then you have, so if the component is heavier, the line just is shifted down, okay, and it has maybe a different slope. But it goes linear and then it starts to have some curvature. Okay. And then at some point, what happens if I, let's say, increase, I have a mixture, right? Then I increase pressure. So let's look at the phase envelope, okay? Let's make the phase envelope. I cannot use it much for engineering calculation, but for analysis is very nice, okay, for making an analysis. So let's say that the fluid that I have is an oil, okay? And this chart is made at constant temperature. So initially I have a mixture, okay? And then I see how it splits, okay? What is the mole fraction of each component in each phase, and I calculate the ratio, okay? Then I increase pressure. What will happen eventually? What I'm going to touch or what I'm going to meet? In this case, right, if I start to go up and up and up and up, I'm going to touch the bubble point line, right? What happens after that? No, in this case, I have liquid, right? I'm going to start having liquid. That means K becomes undefined, okay? Xi, at this point when I touch here, Xi becomes the same as Zi, right? I don't have any more gas phase. So the mole fraction I have of Z, of methane, should be the same. If I only have liquid, the liquid should be the same as the mixture, okay? At that point. So at that point, this K factor becomes undefined. Okay, let's say that this is that bubble point. Okay, PB. Okay, let's call it P bubble point, PB. And that's it. The only Now, something interesting happens when I go and I do that experiment at the critical temperature. Okay? If I do it exactly at the critical temperature, what they saw actually, okay? So let me just, I don't know what, should I spoil this one or let's make a new plot, okay? If the plot is made TC, okay, at the critical temperature, then again, the same thing, I was getting a line, straight line, straight line. But what happened is that I had this behavior, okay? And all of them met, that's number one. Then I had 10, 100. Okay. Okay, so what happened is that all of them at the critical temperature, they converge to the same point. Okay, all of them cross and all of them have, go exactly match into that point, which at that point they have the critical temperature. Okay, and it becomes exactly equal to 1. That means that the critical point is K, this equilibrium ratio, becomes that I have the same fraction in both phases. Okay, the same fraction in one and the other. Okay. So that was, that was, so the way was that people start to make charts, okay, to try to map this equilibrium ratio to see how it looked like for different. This chart is a function of, so it's a function of, okay, it's a function of, we're going to see later, okay, but it's a function of first pressure, right? If you change pressure, you're going to change the number, but you're a function of temperature, a function of pressure. And when it stops being linear, when you start having some curvature, then you have some dependence on composition, okay? Then you have some dependence on the composition, okay? But people try to make, let me show you a chart. You have a chart from before, okay, how it looks like. Okay, here you have one, but they are equilibrium ratio. Okay, like this one. It's not the best quality, but you see here you have, yeah. If I can find a better one. Okay, here you have some examples. Here. Okay, you see that that it has exactly what the behavior we were discussing before. Okay. So what was I saying? Okay, that these charts were made for to allow you to make computation, okay, of this how much I'm going to split, and we're going to see now how to make it. But how much this ratio, people say we can use it to calculate how much is splitting into the gas and how much is splitting into the liquid. Okay? And eventually people came with try to represent this data with an equation. Okay? The thing is that the equation, and that's a bit tricky, the equation was made in a way that first the equation has to cover at least this case, right? The critical point case. Therefore, the curve all of them had to meet in this point. Okay. The shape of the equation they use also does the same for other temperatures. Okay. That means that even here I'm not, I don't have a mixture anymore. Okay. Still the equation is going to do exactly, is going to exhibit that behavior. Okay. Just because the shape of the function had to cover this case. Okay. Then, then for all other temperatures, it made exactly that behavior. Now they found that something interesting, that here, even though I don't have to use, or I don't use at all, okay, any of these data, because simply there is no mixture there. You have either liquid or either gas, okay? But they say here we can define, it's not the critical pressure, but it's a variable called pK, which is the convergence pressure. Okay? And then they say, well, if I change that number, okay, then I can get a better approximation of the experimental data. Okay, I can change that convergence pressure number, until I exactly match, let's say, the points I have measured in the lab. Okay? They say that they are something like this. Okay, I can exactly change that number, that pK, until I go through all of those points. Okay, so that's why this expression is also a function of that convergence pressure, okay, of that pK. But remember, only exists physically at the critical point. At the critical point is the only temperature at which all the lines they match, okay, they meet each other. But at all others, it stops existing after either the dew point pressure, if you're here, okay, if you go up, you meet the dew point line, okay, and then you have no more mixture, okay. But you use that pK to adjust, to change until it matches the data that you have measured. So you say, okay, that's nice, but why? Why do I care about this? About this K ratio. So let's see how people use this K to estimate how much oil and gas we have. First, do we need a break? Yeah. Okay. Let's say 15 minutes. Okay. Go back to our problem. So let's try to specify very clear what do we have. Okay, so what is given is pressure. We provide temperature. Okay, that allows me to calculate this Ki. Okay, for each component. I have either a table, I have an expression, I have something where I can calculate this equilibrium ratio, and then I have the composition set I. Okay. And the main task is to calculate Xi and Yi. Okay, that's what I want to calculate. How they split, how methane splits in between liquid and gas, how propane, every component, how do they split? Okay, so let's see first the number of equations we have. So if we say that we have, if there are n components, okay, so we have how many equations? Okay, let's see first how many unknowns. Okay, we have 2 times n unknowns. Yes, okay, because we have xi and yi, so that's what we have. So how many equations do we have? Well, we have a series of equations, right, which are ki, yi divided by xi. Okay, there we have, if ki is given, okay, then I have n equations. Okay, so I have n equations. What else do I have? Okay, I have, first I know that the sum of yi should be equal to 1, right? The sum of all the fractions. These fractions are divided by the total number of moles in the vapor. And I have the same thing for the liquid. Okay, so here I have one equation, and I have one additional equation, but I still need n minus 2 equations. Okay, I still need I still need, a few more equations. So we know that there is a relationship, right, between xi, yi, and zi. Okay, they are related somehow because they partition. I have like a mass conservation. If I have certain number of moles that one of them goes to liquid, one of them goes to gas, then number of moles in the gas and in the liquid, they should give you equal to the total number of moles of that component. Okay, so that's what we are going to try to do now. Okay, so we say number of moles of a component I will be equal to the number of moles in the vapor of component I plus the number of moles in the liquid of component I. Right? That's simply mass balance. You're saying how much that total composition goes to vapor and goes to liquid. Okay? But how do we get what in reality what we want is to convert this one to Zi, we want to convert this one to Yi, and to convert this one to Xi to have, this additional equation that we need. Okay? So we can simply divide the first step. You can do it in different ways, but I'm going to divide by n total, the total number of moles that we have of everything. So then we say Ni divided by Nt will be Nvi divided by Nt plus Nli divided by Nt. Okay. This that I have here on the left, what is that? Zi, right? I got it. That's one, achievement. And then I have the rest. So here I'm going to introduce something that just is, it's like this quantity that we discussed before. It's called the vapor fraction. Okay, and the vapor fraction, I say, is the total number of moles of vapor divided by the total number of moles. Okay, and this I know by the letter Fb. Okay, is vapor fraction. So I can say that Nt will be equal to Nv divided by Fv, right? And this number should be a number between 0 and 1, right? If it's 0, it means that everything is liquid. If it's 1, it means that everything is vapor. So we substitute here by Nt, and we get Nv, Nvi, and we get, what else do we get? Fv. And this guy is Yi, right? Now we have the last one. Well, we can say that N of liquid divided by Nt is 1 minus Fb, right? Okay, because it will be like liquid fraction, Fl, and the liquid fraction is simply 1 minus Fb. Okay, so we substitute that again here, and we have N liquid of component I, 1 minus Fv. Okay, and at the end, I end up with this equation, which is like a mass balance equation, okay, which is the one that is actually helping me to close the system. Okay, Fv plus Zi 1 minus Fv. Okay, and now do I have enough equations? The same number of equations as unknowns? Yes. Yeah, it's yeah, that's correct. Sorry for that. It's Xi. Okay. So now let's count, okay? We have, let's go up, okay, to see the number of equations we have. We want to know the splitting, okay? Xi and Yi. So these are n, okay? If we have n components, let's say 3 methane, propane, and heptane, okay? We have 3, and here we have 3. We have 2 times 3. That means we have 6 unknowns, okay? We have here, if k is given, someone did the job in the lab, okay, to measure all of these points, to measure this curve, okay, this equilibrium ratio. Then we have n equations, okay? We have this k for methane, propane, and heptane, okay? So we have 3. We know that the sum, here we cannot assume any number. The sum of these numbers should give me equal to 1, and also the same thing here with xi. Okay, so here I have one equation. Now let's see how many equations do I have here. Here I have n equations, right? And but am I bringing any new unknown here? Fv, right? Fv is going to be a new unknown, but it's going to be only one. Okay, so let's sum up to see if we have. Let's see. Let's make a table. Okay, I think it's nice to make a table where we put here unknowns, and here we put equations. Okay, we have Ki. I have 2 times n, and I have n equations. Okay, then I have the sum of yi, that is no new unknowns, but I have one more equation. The sum of xi, no new unknowns, but one more equation. And the last one, which is zi fb yi plus 1 minus fb xi. That will give me how many unknowns? One unknown and n equations. Okay, and I have more equations that I need. Okay, something happened. Do we have 2 more equations, right? Here we have 2n. So what happened? Milan made a mistake, or I think at the end, I think the issue comes because we have to use only one of these 2 equations, okay? Because if you use this one, let's say you assume x, yi, and then you multiply by k, you're going to obtain x1, okay? Without using this extra equation, okay? I think that's where it comes from. But I will check with my notes and then let you know, okay? So let me just remove that. If we use one, and we use this equation, we cannot use the other, okay? I think that's the reason why. But let me just check, okay? But basically I have a system here. I have two equations, 2 times n equations plus 1, and 2 times n plus 1 unknowns, okay? Thus the system is consistent. 2 times n plus 1 and 2 times n plus 1. Now, to solve this system of equations is very tricky, okay? Because you have to assume, let's say you have 10, 15, 20 components, you have to assume all of them, okay? And then you have to iterate with all of them. I guess you learned how to use Newton-Raphson before, right? A numerical method course. So if you have more variables, it becomes more difficult to, to solve that problem. So people were working with that problem, how to make it easier, especially in the 1940s. Okay, they didn't have Excel or MATLAB or computers yet. Okay, so they found a way, and these were two. I think they were from Exxon, Rachford Rice, and that's the procedure we're going to use now, and that's the procedure many simulators use nowadays. Okay, which is a simple way to solve this system of equation. Okay. There are many ways, you can choose whatever you want, but this was one of the most efficient methods to do that. Okay, it's called uh, Rachford Rice problem. The way it is solved, they come to set I using this equation. Okay, fv yi plus 1 minus fv xi, and they substitute in this equation ki. They substitute yi. And you'll see now what happens, okay, which is very clever, how to solve this problem. Ki times xi, they substitute here, set I, okay, then I take as a common factor xi, so I say xi, okay, and then I say that xi will be equal to set I divided by fv, okay. Yeah, let me check if I didn't make any mistake. I have a minus in the one, why? Yeah, I think it's okay. Okay, so the next step is to say that I know that the sum of xi from I1 to n will be 1, right? And the sum of from y1 to n of yi will be 1, okay? Therefore, the sum of yi minus xi should be from y1 to I1 to n should be equal to 0, right? But at the same time, I know that this yi will be ki times xi. Okay, therefore, I can say that the sum I equal to 1 to n will be k I minus 1 times xi will be equal to 0. Yes, let me just make it here. You have to be sure I'm not making any mistakes, okay? I have the final expression, but in the way I might be doing some mistakes. Okay? Therefore, what I can do using that expression, I can simply multiply this expression by ki minus 1 times xi. Simply that will give me ki minus 1 times zi divided by fb ki plus 1 minus fb. Okay, and then I just sum all components. Okay, then I just make the sum both sides. So then I say the sum of ki minus 1 xi from I equal 1 to n, that will be 0, right? And that is equal to the sum of I 1 to n of ki minus 1 zi divided by fv and voila. Okay, and that's the expression, that expression here to the right, that's what we call the Rachford Rice material balance expression to perform flash calculations. Okay, and if you see, you say, wow, what is so nice about this expression? I removed completely xi and yi from the equations. Okay, I don't have to be iterating with xi and yi. I just have ki, which is an input, okay, something that I read from a chart. I have zi is also an input, okay, and I also have to iterate with the fraction. Okay, so the fraction is the only number I use. I use only one number, and then solving this equation allows me to find everything else, okay, which is a very big gain. Okay, so actually, let's now do an exercise in the time we have left, and I'm not sure if the Marcus he will come today, but if I would suggest you to work on this exercise on the session today. Okay, so let's go. If you go to my website, you will see. Let's make a class exercise, and that you have also to deliver. Okay, it's on class files. Okay, it has the date of today. It's called flash calculation exercise. And we're not going to use all of it, only part of it. So let's open that. Okay, that part we are not going to use it yet. Just first separation process. So we have a separation process of high pressure, medium pressure, and low pressure. Okay, here you have the pressure and the temperature. And you see that the inlet composition to the separator is this one, 0.5, 0.2, 0.3. Okay, I did it very simple. We have a lot of components. We are going to have now only 3 just to make your life simpler. Okay, but you can use the same procedure for multi-component. Okay, and the idea is that you have to find the x and the y for each stage. Okay, how much it separates in each stage. So you see here on the bottom, at the bottom, you have Rachford Rice. Okay, behavior. So you have first remember what do we need for, so that's this Rachford Rice function. Okay, zi xi, what we have deduced so far. So we need this k. Okay, instead of reading from a chart, we're going to use an equation. That was that equation that I told you, tuning the data. Okay, you try to match this pk convergence pressure to go through the data. In this case, pk is 689, and we're going to use that expression. Okay. Um, so on this sheet, okay, let's first copy the data from the separation process. Let's do the first stage, the unit to the first stage. Okay, we have 50 bar and 70 Celsius. So where do I copy that here? 50 bar and 70 Celsius. Okay. And then I have the composition. Okay, I can copy the composition from here. And to paste it, I have to be careful. Has to be transposed. Okay, so I go pressure, only values, paste and transpose. Okay, 0.5, 0.2, 0.3. So now the first step is to calculate this K, okay, the splitting ratio. So the expression is using pressure, convergence pressure, is using the critical pressure of the component, okay, separately, which I have. It's using the W is the omega is the eccentric factor, okay, it's another property of the fluid of each component, which I have here. And the reduced temperature, what is it? Is the temperature divided by the critical temperature of the component. Okay, so it seems like I have everything I need to calculate K. Now, to avoid an A2, which is an exponent, we're going to use in this case 0.8. That was the value that better matched the results, okay, measured in the lab. So in this case, instead of you typing that equation here, which might lead you to errors, we're going to use this famous BBA module, okay? So if you punch Alt F11 on this sheet, you're going to get the following, okay? You get these three to the left. You see here I have the name of my Excel file, okay? Flash calculations exercise, version 1. Inside, I have all the sheets that I have, okay, that I have 3. But then below, more interesting, you have something called module. In this module, it's like a repository where I save any mathematical expression, any function that I can use in my Excel sheet. Okay? So if you click on Rachford Rice, you see all the expression that I have here. Okay? I have Ki, this expression was by a person called Wilson, okay? Modified. But I have also Xi, I have also Rachford Rice term, okay? I have a few, and you can write your own equation, okay? You have to use the same syntax. First note that you have to put the name of the function, okay? You have to assign it a name. That's how we're going to use it in the Excel sheet. You have to say the input, what it depends on, that function, okay? And inside, you can do all kind of things, okay? In this case, it's just one line. But you can do all kind of operations. But you have to say, what do you do with the input? And you have to write here, use the same name for the output as the function. Okay? We're not going to do it now. You can do it later if you want. But for now, we are going to use the equation the way it is. Okay? We're going to use this Ki Wilson modified. Okay? To use it, I come here to call the function, insert function. It's a function that I create, okay? It's not available in any Excel, it's just on my Excel. So I have to go down to user define, and I have to find this Ki Wilson. Ki Wilson modified, okay? Pressure, the pressure is here. Temperature, I have to check the units, right? But let me just fill it and then we check the units. pK is here. Critical temperature is here. Critical pressure is here. I'm doing it for methane, okay? And lastly, I need the eccentric factor, and it gives me 10, okay? So if you click on the function, it tells you it depends on all of these variables. Now I want to apply the same equation here, right? But I want to apply now with the conditions of propane and the conditions of decane. I can drag it down, okay, and let's see what happens. I get an error, okay? And why is that? because it's shifting also this one down, okay, and it's shifting also these two down, okay. So what I have to make is I have to come here and I have to block some cells, like pressure and temperature. They should be blocked because all components are under the same pressure and temperature, and the convergence pressure should also be blocked. But the rest, which are property dependent, component dependent properties, they should be fixed. What does it mean that K is high for methane and is low for decane? Does it have any meaning? Remember that is the ratio between mole fraction in gas divided by mole fraction in liquid. Okay, that tells you something, that methane likes to be more in the gas, right, than in liquid. So that's why it's slightly is bigger. Okay, and decane likes to be more on the liquid than being in the gas. Okay, but that, at least like a rough quality control, that's okay. Next, what do we do? So we have to use that equation, right? We have to sum that term for every component. Okay, so let's see. I think I have this equation here. Let's check the units. Okay, the units have to be in bar, temperature and pressure, and Kelvin. Do we have the temperature in Kelvin, the critical? Yeah, it's in Kelvin. Okay, so now we have to use this Rachford Rice term. Okay, which tells you Zi Ki minus 1, 1 plus Fb times Ki minus 1. Okay, so that's the equation we need. We are going to calculate component by component. And I can call the function not only pressing Fx, but I can just say, write it with the name. Okay, Rachford Rice term. And then I select it. And if I want to see the input, I click here on the function. Zi, Ki, and the fraction, which this should be empty. Okay, that was my error. But let's select that. 1.5. And okay, here I should block the FB. Okay, the FB should be blocked. And I drag it down. Okay, and at the end the sum should be 0. Okay, that's what Rachford Rice requires, for the sum to be 0. That's it, right? Simple. Easy peasy. What should I do next? Okay, essentially I don't need anything else, right? I just have to change this number until this number goes to 0. Okay, essentially I don't need anything else. But the idea is that I want to find xi and yi. Okay, that's the whole purpose of the calculation. So how do I find, I think we can use some of these equations to calculate, okay, we can use maybe that equation to calculate xi. Okay, so let's use that equation. I don't think, maybe I have it programmed here. Xi is Zi divided by Fb times Ki minus 1 minus 1 plus 1. Yeah, so that's the equation we need to calculate Xi. So let's use that equation. Xi Zi is here. Fv I have to block. Okay, and Ki is this one. I'm gonna bring it down. And it should give me how much? 1, right? the sum of all fractions should be 1. Letting me do all the work. Okay, and it's not, which it makes sense because the solution is not yet fully converged. Okay, it's actually that number is not the solution. Okay, so let me check 0.24 yi. Hmm? Yeah. So yi is ki times xi, right? So then I bring it down, and then I go to the right. Okay, and still it's not equal to 1. Now, be careful, that function that we are going to solve now is a bit tricky, okay? Because the function looks a bit like that. So this function, let's say that that's called h, has a function of fb, okay? That function looks like this. Okay, it's like start to go down very sharp, and then it goes like that. Okay, but the thing is that it's very challenging for a numerical method because sometimes the slope very close to the intersection can be very steep. Okay, and for methods that work with derivative, okay, they find, like Newton-Raphson, they find the next point by using the derivative. Okay, so if the derivative is too sharp, or I have a very big change of direction, it can give me an error. Okay, so something that helps on that process is to define, like, to bound the function, okay, to see where that root should be. Okay, so people made analysis of this function for a long time, and they found that you can define an fv max and an fv min. Okay, that will be h. Okay, an fv min. Okay, and they say this fv max is 1 divided by 1 minus k max, okay, and 1 divided 1 minus k min. From all the case, for all the components that you have to take the minimum, and then you calculate this number. And from all the case, you take the maximum, and then you calculate this fv max. And this tells you there is a solution between these two. Okay? So that's what we're going to use on top of it to help to get a solution. And I think that's the equation we have here. Okay? So for that, fv min will be 1 over 1 minus, to find the minimum of a list, I use the function minimum in Excel, right? Minimum of this one, which will be the last one. We have to make it general, okay? Sorry, it's the other way. It should be K max, K min, and K max. So this should be K min. Sorry for that. And this should be K max. Okay, so let's see here. It will be, here I should use the max, okay? Max. And here I should use the min. Okay. Now I ask you, can I get a number, an FB, which is not in between 0 and 1? Could that happen? You might say no, right? I cannot, it shouldn't happen. If I have a mixture, okay, it shouldn't happen. But what happens if I have no idea, right? I'm testing that composition, and maybe that composition is in liquid or is in vapor. In that case, I might get an FB which is outside of 0 and 1. Okay, so I have a few outcomes of the Rachford Rice process. Okay, just for you to keep in mind. Okay, typically we should be doing that only for when we have a mixture. Okay, when we have a separation process. But if not, so Rachford Rice procedure, okay, could give, which is the most common case, okay, and that's what we typically have always, between 0 and 1. That means I'm in a mixture, okay? I have both vapor and liquid in mixture, okay? The other option is that FB gives you exactly equal to 0, or that FB gives you exactly equal to 1. That means that I'm in saturation exactly. I'm at the dew point or I'm at the bubble point line, okay? And that means I have saturated liquid or saturated gas, okay? Or I might have that FB is smaller than 0, or that FB is bigger than 1. That means that I have here I have liquid, okay, under saturated liquid and under saturated gas. So be prepared. Sometimes you don't know beforehand, and I'm going to tell you tomorrow how do we deal with that. Okay, we are not sure if we are in a mixture to start with. Okay, but if you obtain an FB which is non-physical, it goes outside of the bounds. That's a strong indication that you have a single phase. In that case, it doesn't make sense to make Rachford Rice, right? FB will be 0 or 1, and then XI will be ZI, or YI will be ZI. Okay. Okay, so let's try now to solve it. Okay, I don't guarantee it's going to solve, but let's try. Okay. Okay, for that we use our Excel has a module, has equation solver called solver. Okay, has any of you used solver before? No? Okay, to get it probably won't be active in your computers by default. So you go here to options, you go to add-ins, okay, you click here go, and you have to have it ticked here. You have to choose it. Okay, in Norwegian problem lesser, in other languages I think it's solver. Okay, so you have to tick it, and then this last button here will appear to the right. Okay, solver. Okay, and solver basically it helps you, like if I want to do it manually, right, I will have to change. Let's try here and see. Here it gives me 1. Okay, so let's try to make it smaller. Let's try with, for example, 0.5. It became smaller, right? So let's put now 0.50 to, it's becoming smaller, but slower. 53. Okay, it's becoming smaller, but it's very painful, the process. Okay, so we can use a computer to make that process automatically. So I come here to solver. I say, what do I want to drive? Okay, to 0. So I select that cell. Okay, I want to make it a value of 0. Okay, that's what I want. And then I want to change what number? This FB. Okay, and to help the solver, to help the computer, I'm going to say, well, FB has to be between these two. Okay, so I come here and I say FB has to be smaller than this guy. Okay, add one more, and this one has to be bigger than this guy. Okay, and then I try to solve, and that's the solution. And typically the tolerance that we need is something very, very low. Okay, that's I think to the -9 is maybe on the limit. I think at least should be less than 1 to the -8. I think 1 to the -8. Okay, but you see here we have a solution where We found xi and yi such that the sum of each one of them gives you 1. Okay, we found a fraction which is physical, okay, something between 0 and 1, and for that inlet composition. Okay. So now what you have to make for the exercise, okay, you have to copy that. So xi, you're going to copy here. Okay, let's transpose values. And you have to copy this one. And the FB, which is here. Okay, and at least it makes sense somehow. Okay, we have a splitting which is more or less half and half. Okay, I had initially entering into the separator, I had like half and half of liquid and gas. I have that the gas has a high content of methane, okay, and a low content of methane, which makes sense, okay. And the liquid has a low content of methane and has a high content of decay. At least that's how you make a very rough quality control. What is the next step that you will have to do now? You have to remember the liquid separates, and that liquid is what goes to the second stage. Okay, so you have to take the liquid composition, that will be the inlet composition of the second separator, and you have to repeat once more. Okay, and you have to do that 3 times until you find the composition of liquid and vapor for all separation stages. Okay. Then tomorrow we're going to see how do we use, remember, composition gives you the fingerprint of the fluid. Then we can calculate density, entropy, whatever we need for our estimation, for our engineering calculation. Okay, but the first thing we need is that composition. Okay? And what we have done today in class is we are relying on this K. Okay, we are using an equation for K, which we is not something that can be used for process very low pressure process calculation. Okay, we're going to see tomorrow. We to make it more generic, we should use yeah, we should use an equation of state. Okay, but for now we say we're using low pressure, we're using K values, and this is good enough for to make our calculation. Any question before we close? No? Okay, see you tomorrow.